This is work, as was said, is a joint work with my scientific advisor Andrei Igorevich. So, and it's Gaussian beam solutions to the Cauchy problem for the Schrodinger equation with a delta potential. Okay, first of all, I want to say about the plan of my talk. I want to formulate the problem, to say a few words about canonic system and mass of complex germ theory, and then to consider two cases: the case of a smooth potential and the case of a delta potential. We study Gaussian beam scattering on a delta potential. The delta potential is localized on the surface of codimension 1, and the initial data are represented in the form of a Gaussian wave beam. So it is described by formula 1.2, and this is a quadratic function, quadratic complex function with the imaginary part that is greater than 0 and equal to 0 only in one point x0. So here only B0 is a complex symmetric matrix. These initial conditions means that our initial Gaussian beam is localized in the small neighborhood of point x0. And it is well known that Schrodinger equations are solvable only for some potentials. So that's why the asymptotic theory is really well developed. One of the ways to construct the solution is to construct a semi-classical asymptotic. So these methods are really well developed, and but they are not really well developed for the singular coefficients. It is connected with the fact that Maslov's theory is developed only for smooth coefficients. So we want to describe the semi-classical asymptotic for this Cauchy problem. So because we are talking about the Schrodinger operator with delta function, first of all, I want to define this operator. This operator is defined as a self-adjoint extension of the operator of the Schrodinger operator with smooth potential, restricted to the functions vanishing on the surface M. So this is requirements, and it means that this operator requires boundary conditions on the surface M. So the first condition here is a condition of continuity of psi function. Here is psi is a solution, and other one is describes discontinuity of normal derivative. Derivative, yeah, thank you. Normal derivative. So, and if we're talking about Schrodinger equation, I want to consider the general case when we have a non-stationary Schrodinger equation with smooth functions. So in this case, we can construct the solution in the form of Weber function. So here all functions are also smooth, and then we can put this formula 1.5 to the our Schrodinger equation, and then we will have following equations. It is Hamilton-Jacobi equation with initial data and transport equation also with initial data. So this is how we can reduce the construction of asymptotic to the solving two types of equations. So the theory of Hamilton-Jacobi equation is connected with special geometric objects called Lagrangian manifolds. So, and we can consider this Hamilton, and it is generate a Hamilton system, and the initial phase S0 generates initial Lagrangian manifold lambda 0. So you can see it 2.2. So, and then we can shift this Lagrangian manifold by translation along the trajectories of the Hamilton system. So then we construct the family of Lagrangian manifold, and this Lagrangian manifold I will use lambda for this. So on this Lagrangian manifold lambda, we can write the action, and the action will be a solution for the Hamilton-Jacobi equation. So in our work with complex phases and delta potential, we will use following estimations. We'll use norm 2.5, and all estimations that you will see are made in this norm. So, and also I want to construct some definitions. The first is definitions of the approximate solution of the Cauchy problem of the Hamilton-Jacobi equation. So if the phase satisfying following equations, we will call it an approximate solution. And also I want to say about the solution of the Cauchy problem to the transport equation. So if these estimates are true, then it is an approximate solution. So these terms I will use. Okay, for the construction, the solution in the case of complex phases, we can use the method developed by Maslov that is called the method of Maslov complex germ. The difference in this construction is that before we used to consider Lagrangian manifolds. Here we consider Lagrangian manifolds and complex germs. So let's define complex germ. Let's consider lambda is a Lagrangian manifold, and then for every point sigma of this Lagrangian manifold, we will consider complexified tangent space. So then, for each point, we can assign tangent space such as it is contain the complexified tangent space and satisfy the following conditions. So this subspace is also Lagrangian, and the following solution also are true. This solution we need. So I will talk later. I will say later why we need this solution or this condition. Yeah, this pair of Lagrangian manifold and complex germ is called Lagrangian manifold with complex germ. So let's construct a asymptotic solution in the case of the small potential and with complex phase. We assume that our phase is represented as Gaussian beam, and the initial condition satisfied this estimate. So we also will construct the solution as a Jacobi function. So if we will try to find solution in this form, we will achieve the following. We can consider trajectories of Hamilton system. Here you can see these trajectories. That's important that these trajectories, initial data from them is localized only in the one point in the phase space. So the initial Lagrangian manifold is only one point in the phase space. So, and then let's consider the variational system. Yes, the variational system is also defined by this initial data, and we introduce the function, the matrix function Q, that is equal to composition of matrix B and inverse matrix C. So, as I said, our initial Lagrangian manifold is only one point, and our R0, it is our complex germ. It is defined by these conditions. So that is how it is defined. So what we have one point and a complex subspace, tangent subspace in this point. So, and then we will define the shift of the Lagrangian manifold with complex germ. So this is a shift. And we construct the family of Lagrangian manifolds and complex germs in the different times. So then we can define the action on this Lagrangian manifold. It is defined by formula 4.9. So, and of course, this action on the Lagrangian manifold with complex germ will be a solution to the Hamilton-Jacobi equation in the case of complex phase. So, as I say, this is a solution of Hamilton-Jacobi equation, approximate solution. Okay, and then we can consider the transport equation. The first equation, so it is a transport equation with right parts for the main member of asymptotic. There are no right part, and for others we have these right parts. So, and then we can define following functions. Using these functions, we can construct functions phi of x and t. And this function is a solution of the transport equation, approximate solution of the transport equations. So this is a theorem from Maslow's books, but with different estimations because we use different norm. So then, if we have solved the transport equation and the Hamilton-Jacobi equation, we constructed an asymptotic solution for the Schrodinger equation with a smooth potential and complex phases. So it can be represented in this form, and this estimate is correct. So n is a number of members in our asymptotic sum. Okay, then let's construct the solution in the case of a delta potential. In the case of a delta potential, we have three waves. It is falling wave, rejected wave, and passing through the surface M. So that's why we're searching the solution in this form, in the form of three waves. So here, first line is defined on the negative side of the surface M, and plus it is a falling function, and minus is rejected. So, and hat is for past wave. So we will assume that phase is also, as it was before, represented as a Gaussian beam. And if we will, as you remember, we need to satisfy boundary conditions on the surface M. If we will put this function in our boundary conditions, we will have follows conditions for the faces. So this is continuity of faces on the surface M, and we can see that the normal derivative for the reflected wave changes its sign. So as we remember, our solutions for the Hamilton-Jacobi in the case of a smooth potential depend only on time. They don't depend on space coordinates. So that's why if we want to define boundary conditions, we will define them in the point t0. T0 is the moment of intersection, and we assume that our trajectory of the Hamilton system cross the surface M only one time. So, and of course, for the falling wave, we will have the same formulas as for the wave in the case of a smooth potential. So I use here also x and p as it was before. So I can say that for the passing wave, we will have the same phase. So, and this is the question: how to define the conditions for the rejected wave. So for the impulse, we have these conditions. So we assumed these conditions, and then we will describe sigma function. Sigma function is a solution of the Hamilton-Jacobi equation, and it satisfies these boundary conditions, but boundary at the point t0. So, and that's the main question is how to define the solution of the variational system. Okay, for the falling and for the passive waves, phases are the same. That's why we define them as before. So, and if we want to define the solutions of the variational system in the case of the rejected wave, to do it easily, let's represent impulse in this form. So here M is a normal component, and sigma is a vector from tangent space at the point. I said here at the point A. The point A, it is this point, x of t0. So if we represent impulse in this form, we have following conditions. So I divided these conditions on two parts. One part is for imaginary part of matrix Q, and the other conditions will be for the real part. So here you can see these conditions. And here the conditions for the real part of matrix Q. They're really similar, but you can see that first line is different. Here we have a shift on the derivative on this vector. So, but of course, because these solutions of the variational system and also for the trajectories of the Hamilton system are defined at the point t0, these functions are not the exactly right solutions of our equations. So that's why we want to correct our phases. We will define function W by these conditions. So if we define this function on the surface M with these conditions, then we can correct rejected phase on this function, and the estimate for this function is such that it doesn't ruin the approximate solution. So we need this to exactly satisfy boundary conditions. I want also to say here about these conditions, that these conditions for the matrix Q are the conditions for the variational system for the matrices B and C. And these solutions, these conditions define complex germ. So then we need to write the solution for the transport equation. And for the transport equation, we will define our functions also on the surface M. So with these conditions. So we constructed the solution of the Hamilton-Jacobi equation, and we constructed the solution of transport equations. So that means that we constructed the solution of the Schrodinger equation with the delta potential and complex phase. So, and we have following estimates.